Poisson probability distributions. The Poisson probability distribution is a binomial distribution. We use the Poisson probability distribution to estimate the binomial when the probability of success is very small and the n, which is the trials, are very large. This is often referred to as the law of improbable events because the probability of success is very small and unlikely. The Poisson probability distribution describes the number of times some event occurs during a specified interval. The interval may be time, distance, area, or volume. Only the mean average is required to figure a probability. From actuary tables, Washington Insurance Company determined the likelihood that a man aged 25 will die within the next year is 0.0002. If Washington Insurance sells 4,000 policies to 25-year-old men this year, what is the probability they will pay on exactly one policy? This is a binomial. It's a binomial because we have a discrete probability distribution. We have a constant probability of success, and it was here in our story problem, 0.0002. We have a known number of trials, our n, of 4,000, and we're looking for exactly one success, and one success is one man dying or paying on exactly one policy. Instead of using the binomial distribution to solve this probability, we're going to use the Poisson distribution. The reason is the probability of success, and this is the probability of success, dying is the success in this example, is really small, and the number of trials is large. When we have small success and large trials, we can use the Poisson distribution to estimate the likelihood of a particular event. Let's do this first by using the formula, and then we'll make it easy on ourselves and use the table. Here is our Poisson distribution formula. Let me go through it for you. To figure the probability of a particular number of successes, we'll take the mean average, which is the mu, to the power of x. That was our number of successes. We'll multiply that by the constant e, and the constant e is down here. The e will always be 2.71828. We'll take that e and we're going to take it to the power of negative mu. When we've multiplied these two together, we're going to divide by x factorial. This formula is going to require us to know the mean. So I'll write that here. Here's the mu. Remember that for a binomial, if we take trials times success, that will give us our mean. Trials are 4,000 and success is 0.0002. Our mean average is 0.8 for this problem. Remember that the mu in a binomial, or in a Poisson now, is the expected value, or what we would expect to happen. In this particular problem, we would expect 0.8 of a man to die within the next year. So this company would pay on 0.8 of a policy. We're asked to figure the likelihood that exactly one man dies. 1 is our x. We'll begin by taking the mu, 0.8, and taking it to the power of the number of successes, which is 1. We'll multiply that by our constant e, 2.71828, to the negative mu, and the mu is 0.8. We'll divide that by x, which is 1, factorial. Some of you will be able to plug this into your calculator and figure the answer right off. But if you can't remember how to plug a negative exponent into your calculator, one way to get rid of the negative exponent is just to move this down into the denominator. So I'm going to move my 2.71828 into the denominator. And when I do that, I can drop that negative on the exponent. And when I moved it, I've got to get rid of it up here. Now we can figure our probability. 0.8 to the power of 1 is 0.8 divided by 1 factorial multiplied by our e to the power of 0.8 is 2.22554. When we divide, we have 0.3595. The likelihood that exactly one man dies and the company pays on exactly one policy is 35.95%. Well, that was a little bit harder than it needed to be. It was a little bit harder than it needed to be because we could have just used a table. And the table is going to follow on the next slide. And what we'll need to find this probability that we figured is we're going to need to know the number of successes we're looking for. And we're going to need to know the mu, the mean, which is 0.8. Here is our Poisson distribution that's in the appendix in your text. To use this, you'll first want to find your mean. Our mean is 0.8, you'll remember. Be really careful and don't pick this one. This one is 8 point. Don't do that. We need to find 0.8. Next, we'll find the exact number of successes that we're figuring. And we were looking for exactly one death. Exactly one is going to be here, and that is 0.3595. Whenever you can use a table, I would do so. In this class, you'll have tables during your exam. Miss Bergen is a loan officer at Coast Bank and Trust. From her years of experience, she estimates that the probability is 0.025 that an applicant will not be able to repay his or her installment loan. Last month, she made 40 loans. We've got a binomial probability. Because the distribution is discrete, we have a constant probability of success. That is that each and every applicant has a 2.5% chance of defaulting on the loan. There is a known number of trials, 40. And in A, we'll figure the probability that exactly 3 loans are defaulted. The number of successes or the number of defaults, that's X, will be 3. This is a binomial, but we can figure it as a Poisson because the number of trials is considered to be large, and we'll say if it's over 30, it's large. Let's use the formula to figure this out first. The probability that exactly 3 loans default will be the mean to the power of successes multiplied by the constant e to the negative mean, or mu, divided by x factorial. We'll need to figure our mean. Our mean is trials times success, 40, multiplied by 0.025 is exactly 1. That's our expected value. We would expect about 1 of these loans to default. The probability of exactly 3 defaults will be our expected value, that's our mean, to the power of 3, multiplied by our constant e, 2.71828, to the power of -1, divided by 3 factorial. Let's get rid of this negative power by moving the e to the negative mu to the denominator. In our numerator, we just have 1. In our denominator, we have 3 factorial. Remember, 3 factorial is 3 multiplied by 2 multiplied by 1. I don't need to write 1 though. Multiplied by our e to the power of 1 which is 2.71828. This is 1 divided by 16.30968. 1 divided by 16.30968 is 0.0613. The probability that exactly 3 default is 6.13%. I'm going to write that up here. Probability exactly 3 default is 6.13%. I wrote that up there because I want to have room for the table. Now we want to look at this answer A. We want to figure the answer for A again using the table. Our mean is exactly 1, so we'll use the first column. Our x is 3, so we'll look for our x, that is 3, and find exactly the same answer. If we have an expected value or mean of 1, the likelihood that exactly 3 default is 6.13%. In B, what is the probability that at least 3 loans will be defaulted? At least 3 means 3 or more. It means 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 all the way to infinity. We'll use the special rule of addition and add these up. Or what we could do is use the complement rule and take 1 and subtract the only ones that we don't want. The only ones that we don't want consist of 0, 1, or 2. Let's use the complement rule. The probability that exactly 0 or 1 or 2 default is 91.97%. That leaves an 8.03% chance that at least 3 loans default. You'll find that's the same number as the total of 3, 4, 5, 6, 7, 8, and 9. Automobiles arrive at the Elkhart exit of the Indiana Toll Road at the rate of 2 per minute. The distribution of arrivals approximates Poisson distribution. What is the probability that no automobiles arrive in a particular minute? I wanted to use this example because I want to reiterate the idea that if we figure a probability using a Poisson distribution, all we need is the mean, that's the mu or the expected value. In this example, that's all we've got. All we're told is that we have 2 automobiles arriving per minute. All we've got is an average of 2 cars per minute. If all we've got to work with is a mean, we're going to need to use the Poisson distribution. Let's use the table right off. Our mean is 2, and we want to figure that the probability of exactly no automobiles. So x is 0. The likelihood is 13.53%. What is the probability that at least 1 automobile arrives a particular minute? At least 1 is 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9, you get it, or 10, clear out to infinity. The only one we don't want is 0. So let's use the complement rule. 1 less the probability of 0 is going to give us at least 1. 1 less, we already figured the probability of 0 right here, 0.1353 is 0.8647. The probability that at least 1 automobile arrives during a particular minute is 86.47%. Let's do one last example. Approximately 8 out of every 100,000 people in the U.S. die of unintentional injuries, that's accidents, per year. Given a Spokane County population of about 75,000 people, how many people would you expect to die in accidents per year? We are asked in this first question to figure the expected value. Remember that that's the mean. So we're not figuring a probability right now. A mean is calculated by trials times success. In this example, we're not given the probability of success. We had to figure it ourselves. Because approximately 8 out of every 100,000 people in the U.S. die of accidents, we take 8, divide it by 100,000, and we had to figure our own probability of success, which is 0.00008. The trials are the number of people in Spokane, 475,000. So the expected value, trials times success, is 38. We would expect 38 people to die of accidents per year in Spokane County. Now, what is the likelihood? So now we're being asked a probability. What's the likelihood of exactly 30 people in Spokane dying of unintentional injuries? We're going to figure the probability of exactly 30 people dying of accidents. Our X is 30. We're going to use the formula. And we're going to use the formula because we don't have a table with a mean of 38. So we're going to need to figure this out by hand. If we take the formula and plug our numbers in, we have an X of 30. Here's our mean of 38 to the power of 30. That's our X. Here's our constant E to the negative mu and X factorial. We're going to get rid of that negative exponent and move the E to the negative mu down into the denominator. And that makes this exponent a positive exponent. When we calculate our answer, we find that the likelihood of exactly 30 people dying of an accident in a year in Spokane is 2.929%.